Alright, so the closest pair problem in 2D. Here the input is a set of n points in 2 dimension, let's say x1, y1, x2, y2 up to x and yn. And our task is to find the closest pair of points in this set. In other words, we want to find the pair of points such that the distance between them is the minimum among the distance between all pairs of points within this set. And when I say distance, it is Euclidean distance here. Alright, so this problem can be solved in quadratic time easily because there are only n choose to different pairs. However, we want to solve it in time better than this, and what we're going to see is a divide and conquer approach based solution with a running time of n log n. Okay, so let's start. Let me first show a small picture. Let's say these are our points in space. The first thing we will do is divide these points into two parts, or divide the space into two regions using a vertical line. Let's say x is equal to m, in such a way that the number of points on the left side and the number of points on the right side are roughly the same. Roughly the same means this side we have roughly n over 2 points, and this side also has roughly n over 2 points. And the way we're going to achieve this is by drawing this line x is equal to m, where m is the median of all the x coordinate values, and median can be computed in linear time, right? So this m can be computed in O of n time, median, right? This is median. Okay, so first step is find the median, split the points into two regions, and let me call these regions as the left region and this is the right region. Okay, now there are three possible cases, right? There are three possible cases. The first case is this. The output which I am looking for, that is the closest pair, will be on the left side, that is both points within my closest pair will be on the left region. That is one possibility. Another possibility is both points within my closest pair will be on the right side, and the last case is one point on the left side and the other on the right side. Okay, so these are the three possible scenarios, and what I can do is something like this. I'll try to find the best pair among all points within the left region. Similarly, I will find the best pair, best means the closest pair among all points within the right region, and I will also find the best pair or the closest pair in such a way that one on the left, one on the right. So I have three answers from each of these sub problems. Then I will choose the best among them. Best means like the smallest among them as my final answer, and this is the approach. Okay, so the first step is find the closest pair in the left region. Okay, and what I'm going to do for this is nothing but recursion. If you assume Tn is the time for solving this entire problem, right, using an algorithm which I am about to invent, and since I am dealing with this divide and conquer strategy, I can assume that this sub problem can be solved in Tn over 2. In other words, the closest pair in the left region can be solved in Tn over 2 time. And let me assume that this is the closest pair in the left region. Let the distance between the closest pair be d1. That is my first step. The second step is again find the closest pair in the right region. Let it be, let's say, let it be this pair, okay, and the distance between them is, let's say, d2. So I already got d1 in this time, and I also got d2, and I need to spend the same amount of time, that is tn over 2, for getting d2. Alright, so now I'm interested to know, what I'm interested to know is whether there is another pair of points such that one is on the left side and one is on the right side, and the distance between them is better than both of them. In other words, I want to find, or I want to basically check if there exists a pair such that one point is on the left region, other point is on the right region, and the distance between them is smaller than both d1 and d2, is lesser than the minimum of d1 and d2, and I'm going to give a name for that, is lesser than d, where d is the minimum of d1 and d2. Alright, so I want to know if there is another pair which can give us a better solution. Okay, so this is what the overview of my algorithm, and these two parts are taken care by the recursion, so I don't need to worry about anything, and that is the beauty of divide and conquer strategy. The only thing I need to worry about is how to solve case 3. Okay, and for this I'm going to make some nice observations here. One thing is this: I'm looking for a pair of points such that one point is on a left region, the other point is on the right region, and the distance between them is strictly lesser than d, which immediately tells me this. Okay, so what I'm going to do is to draw a small line like this. Basically, I will draw two lines such that these lines are parallel to the middle line, and it is at a distance d away from the middle line. And what I can say at this point is this: the pair of points which I am looking for in case 3, if at all there is one, it cannot be in this region, also it cannot be in this region. Okay, so these regions I can ignore. The reason is simply this: if you take any point here, right, the distance from itself to any other point in the right region is clearly more than d. So therefore this point is of no interest to case 3. Similarly, for any point, after this third line is at least d distance away from the middle line. Therefore, the distance from this point to any other point in the left region will be definitely more than d. So therefore, we can rule out the possibility of any of these points being one of the point in the closest pair in case 3. Okay, so now our focus is only on this small region. Okay, and to solve this, here is what I'm going to do. Okay, I'll first explain the algorithm, then I will show you why it works. My first step is this. I will scan this region. And I will collect all the points in this region in the ascending order of y coordinates. Okay, basically I will collect all the points within this region, and perhaps I will just sort them. I'll sort them all in the ascending order of y coordinates, and I get a list then, right? So let the points be P1, P2, P3, P4, P5, dot dot dot. You will have some P50 at some point, P51, dot 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 dot, etc. So all the points in this region in the ascending order of y coordinate. Now what I'm going to do is this. For every point in this list, right, for each point in this list, I will compute the distance from itself to 7 other points which is coming immediately after it. Okay, for every point in this sequence, for example, let's say this point, I will consider the next 7 points, and I will compute the distance from itself to each of those 7 points, right? Then I will pick the minimum. Okay? So basically whatever is the number of points multiplied by 7, right? So that many number of distance computations I will do, and I will find the pair which gives me the minimum distance. Okay? And my argument is that if that minimum distance is smaller than d, then that should be the final output. If that distance is not smaller than d, then just ignore it. Then the output is going to be either the pair corresponding to d1 or d2, whichever is the minimum. Okay, so I hope the algorithm is correct. I will explain once again. I will collect all the points within this region, and I will arrange them in the increasing order of y coordinate values. Then I'm going to do some distance computation. Essentially for each point I will consider the next 7 points. Basically for each point I will consider the distance from itself to the next 7 points. So that means in total I will do as many as 7 multiplied by the number of points, that many distance computations, and pick the pair which gives us the minimum distance. And if that minimum distance is smaller than d, I will report that pair as the closest pair along with the distance. However, if that distance is not smaller than d, I'll just ignore it, right? I'll just ignore it and I will report the pair corresponding to, pair corresponding to either d1 or d2, whichever gives us the minimum distance, as the right answer. Okay, so we'll look at the correctness first, and then we will see how to bound the runtime complexity. Okay, so first part is the correctness. To prove the correctness, here is what I'm going to do. Okay, suppose there is a correct pair. Suppose there, all I need to show is this. Suppose there is a pair with pair in such a way that one point is here, one point is here, and the closest distance between them is smaller than d. All I need to show is during the execution of this algorithm, I will definitely compare those 2 points, right? If I compare those 2 points, I will capture it and I will finally report it as the correct output. Okay, that's all I need to show. So let me imagine that this is actually the closest pair in my output. Suppose this is a scenario. Okay, suppose this is the closest pair. Then what I can show is this. This is a bottom point. This point comes first in the ascending order of y coordinate values. So let me draw a small line, right? So this distance, as you know, it is d. This is also d. So I drew a small line like this. Then I'm just taking a distance d and I'm going to draw a small box like this. Okay, so all I have done now is I drew a small box. With height d and this 2d. Okay. Now my claim is this. Clearly, this closest pair must be within this box, right? Because if it is out of the box, like if it is above the box, that means the distance between this point and that point will be more than d, so it cannot be the closest pair. So this closest pair must be within this rectangle, that is for sure. Now, if you look at your algorithm, if you look at my algorithm, I'm going to look at only the remaining or only the next 7 points. And what I need to prove is that the number of points within this region, excluding this point, is at most 7. That means definitely I will look at this point, right? And to prove this, what I'm going to do is let me just make this rectangle into smaller squares. Okay, so I just cut this into 4 squares, made this also into 4 squares. So if you look at each of this little square, the length of a side is d over 2 and the length of the diagonal is d divided by square root of 2, which is strictly less than d. Okay, so make this observation. And now I am claiming something like this. Within each of these little square, you cannot have 2 points. Okay, within any of these little squares, you cannot have 2 points. The reason is clear from that figure, because if there are 2 points, then the distance between those 2 points will be less than or equal to the distance is less than or equal to the length of the diagonal, which is d over square root of 2, which is strictly less than d. Okay, which is not allowed, because if you look at these little boxes, they are completely in one of these region, and within one of this region you cannot have a pair of points with value less than d by the definition of d, which means in this little box you have this point anyways, and there are only 1, 2, 3, 4, 5, 6, 7 remaining little boxes, and this guy's closest pair must be within one of these little box. Therefore, this algorithm will definitely compare these 2 points and finally give us the output. So that is a proof of correctness. And now the last thing we need to show is how to bound the runtime complexity. Alright, so runtime complexity, if I write something like this, that is T of n, the first thing is I need to find the median, right? So finding the median is big O of n, and once I find the median, I can partition this into Tn over 2. Partition this into two regions and solve these subproblems in Tn over 2 and Tn over 2. So 2 times Tn over 2, then big O of n for computing the median. And once I get this, what I have to do is, sort these points and get this increasing sequence, right? And once I get this increasing sequence, the remaining calculation will take only big O of n time, right? Because the number of points here is at most n, and per point I will do only 7 distance calculation. Therefore, there is a time for sorting and the remaining time is only linear. So if I add the time for sorting, which is n log n, plus another big O of n that I can absorb here, so my Tn will look like something like this. Tn is 2 Tn over 2 plus big O of n log n, and if you solve this, you will get something like log square n. Alright, so this is not what we actually wanted to achieve, right? We thought we can get something like n log n, but we are slightly off, basically off by a log factor. Okay, so how to remove this log factor? That is the next question. Alright, so removing this log factor is not a big deal. All we need to do is pretty much do the same algorithm, but just kind of analyze it in a slightly more clever way. Okay, so what I'm going to do is this. So previously I defined Tn as the time for solving the closest pair problem, and that is how I ended up in getting a slightly bad complexity. So let me define Tn as the following. Tn is a time for solving the closest pair problem and sorting points with respect to y coordinate. Okay, so I actually kind of added some extra work to the algorithm. I want to find the closest pair and also I want to sort them, right? Okay, so what is the advantage of writing something like this? It will be clear in a sec. Okay, now the good part is this. Now I can write Tn like this. The first part is I need to partition this into two parts, right? First I need to spend O of n time for computing the median, that will cost me O of n. Then I will sort this part, then I will find the closest pair in this region, closest pair in this region, which will cost me 2 times Tn over 2, right? And now that I have a definition like this, time for sorting closest pair and sorting points with respect to y coordinates, which means I have these points like n over 2 points sorted with respect to y coordinate, like a sorted list is already ready here and another sorted list is ready here. And to get this sorted list, all I need to do is simply merge them, and the merging can be done in big O of n time, right? And the last step can also be done in big O of n time. So suddenly that extra n log n is gone, and now this recursion is nothing but n log n. Okay, and this is what the solution.